This video is for section 1.4 on polynomials. We're going to start with the building blocks of polynomials. A monomial is a product of a number and a variable raised to a power. So the variable is raised to a power. Sometimes there are variables. They may be raised to different powers, but we're mostly going to study polynomials in one variable. Another name for a monomial is a term. A mathematical term in an expression is exactly the same thing. So here's, to start with, an example. Negative 4x squared is a monomial, and I want to point out some features of this that are going to carry over when we look at polynomials. This number is the coefficient of the monomial, the number factor, negative 4. In this case, let me be explicit about that. It's the negative 4 that's the front part of that monomial. The variable here is that unknown. We've been working with linear expressions a little bit, but the x is the variable. The other important feature, though, is that exponent of 2, that is the degree of the monomial. So this is a degree 2 because the exponent is 2. Let's look at a couple other examples of monomials. So these aren't example problems, they're just examples of monomials. 5.3t. In this case, the variable is t instead of x. I use a cursive t because it doesn't look like a plus sign, which ordinary print t does. The coefficient is a decimal, 5.3. The degree is 1. This is t, which is t to the first. The degree is 1. You could write it like this, 5.3 t to the first, but that's not really simplified because you don't need the power of 1 to indicate one factor of t. Here's another example, xy cubed. So this one has two variables. It's a product of variables. Well, there's a number that we haven't written. The coefficient here is 1. The exponents are 1, this is x to the first, and 3, y to the third. So the degree of this polynomial, or the degree of this monomial would be 4. 1 factor of x and 3 factors of y makes 4. All right, so let's look now at the main topic of this section, a polynomial. A monomial or a sum of monomials. So a monomial by itself is considered a polynomial. Or we can add together different monomials. And that's where that term poly, which means many terms in this case. Here are some examples. First, negative 4x squared. As it says here, a monomial is a polynomial. This is the one that we looked at first, that first monomial. It has one term. Another example, 3x plus 2. That's an example of a binomial because I've added together two monomials. Now the 3x is pretty clearly a monomial. That number 2 is also a monomial. The variable, we don't see the variable. You could think of it as x to the 0 power, which is 1, 2 times 1. But a number by itself is considered a monomial. It just doesn't have a variable factor. This is a binomial because we've added together two monomials. Here's another, 3x squared plus 2x plus 1. That's an example of a trinomial. And I'm going to point out a few things about this one. First of all, this whole piece, the 3x squared, that's called the leading term. And it's not because it's in front, it's because it has the highest power. To write them in descending order means to put with the leading term first. And that's how this is written. The leading coefficient in this case is 3. It's the coefficient of the leading term. All right, so now we're going to get into what we're actually going to do with polynomials in this section, which is combining them, which is a combination of algebra and arithmetic. And the first thing we're going to do, adding and subtracting polynomials is called something you're probably familiar with, combining like terms. So like terms are monomials that have the same variables with the same exponents. They may have different coefficients. That doesn't matter. That's what we're going to actually combine. But we can combine like terms to accomplish addition and subtraction. I'm going to do first, as an example, 2x squared plus 3x plus 9 plus x cubed minus 4x plus 1. And since this is such a wide expression, I'm not going to do the equals and then I can't fit it. So I'm just going to go step by step and simplify it. And with this one, we could just rewrite it by dropping the parentheses. These parentheses aren't actually doing anything as far as the operations go. We could just get rid of them. What we're going to do is combine like terms. Well, there's only one x cubed term, so if I write that first, that's going to put my leading term in the leading term position. Next, I'm going to look for x squared terms. There's a 2x squared, but that's the only x squared term. There are two x terms, so plus 3x minus 4x, that's minus 1x, or just minus x. And then finally, plus 9 plus 1 is plus 10, and that's the sum of these two polynomials. So we added together two trinomials, and we ended up with a polynomial with 4 terms. I'm going to clear some space for the next example so I don't have to scrunch it. So, different example. Let's next look at x squared minus 2x plus 5 minus 2x squared plus 5x minus 8. And a safe and efficient way to do this is to rewrite this expression, the whole thing, without the parentheses. The first parentheses are really doing nothing. I don't have anything to distribute or a power or anything. It's just x squared minus 2x plus 5. But the second pair of parentheses means that I have to distribute a negative. I'm actually subtracting each of these terms. So minus 2x squared, minus 5x, and minus negative 8. I'm going to save a little bit of time just by writing plus 8 there. But minus negative 8 is where that comes from. And now the rest of it is combining like terms, like we did before. There are two x squared terms, so x squared minus 2x squared is negative x squared. Two x terms, minus 2x minus 5x is minus 7x, and 5 plus 8 is plus 13. And that's the simplified, that's the difference of these two. Difference means subtract. So next we're going to look at multiplication of polynomials, and so multiply polynomials means to distribute. And you've done distributing before with numerical expressions. You've probably done it a little bit with variable expressions, but we're going to look at the simple case of distribute first. But there are other situations where we're going to need to distribute and then distribute again. So it's still called distribute or distribution. So let's look at an example of distributing with polynomials. First, 4x squared times 2x. That's multiplying. Actually, there really isn't anything to distribute with this because they're both monomials. I need to just multiply the coefficients. 4 times 2 is 8. And multiply the variable components, x squared times x. To multiply the two expressions with the same base, I'm going to add the exponents. 2 plus 1, this is x to the first. 2 plus 1 is 3. And that's my product is what we're finding when we multiply things. Here's another one that is actually a distribution situation. 3x times 5x plus 1. So what that means is I have to multiply 3x by each of these terms. I'm going to write it out, 3x times 5x plus 3x times 1. But you might be able to accomplish this next step just from here by keeping track of things in your head a little bit at a time. The first two terms multiply to 15x squared. 3 times 5 is 15, x times x is x squared. And then 3x times 1 is 3x. And that's the product. So this is a product of a monomial with a binomial. And you saw that I really had to distribute in this case. So the distributing or distribution is the process for multiplication. The first example, there was only one single product, but this one, to multiply this with this, I had to do two products, and I got two terms. The next one we'll look at is a more complete look at the process of distribution for polynomials. We're going to have a fast way to do binomial times binomial. You've probably learned FOIL in the past. It won't work here because this one is a trinomial. So I have to distribute. There isn't a fast technique like FOIL. The way I'm going to do this one is to distribute this whole trinomial to each term of the binomial. So what I mean by that is 2x times 3x squared minus x plus 4 plus 1 times 3x squared minus x plus 4. I didn't change this one. In a sense, I duplicated it. I wrote it twice, but really what I'm doing is distributing that trinomial to both terms of this binomial. And now is the second distribution. I have to distribute that to these three and that to these three, even though that's really multiplying by 1 isn't going to change anything. But this part, 2x times 3x squared is 6x to the third. X to the first times x squared is x to the third. Minus, because there's a positive times a negative, is negative 2 x squared, because it's x times x. And 2x times 4 is 8x. And as I said with the rest of this, I'm multiplying by 1. It's not going to change any of these things. They're going to appear exactly the same. Plus 3x squared minus x plus 4. So now I can combine like terms. I've only got one term with an x cubed, so that's, and it's the highest power term of all these, so it should be first. If I go to the next highest power, 2, x squared, I've got negative 2x squared plus 3x squared, that's positive 1x squared. Negative 2 plus 3 is how I get that coefficient. And since it's 1, I'm just going to write the variable part. There's two x terms, 8x and negative x. Those combine to 7x. And then there's only one constant term, and that's the product. So this is a full distribution problem. I have to do distribution of the one to the other, and then distribution of the parts of the other. You can do this instead of FOIL, but that's what we'll look at next. That's the fast way to do it with binomials. As I said, it doesn't work with trinomials, but binomials, product of binomials comes up so often that we've got a special technique for it called FOIL, which you have probably studied before, but it stands for firsts, outers, inners, and lasts, plural, all plural. The firsts, let me write up an example so I can point to these things. We're going to find the product 2x minus 10 times 3x plus 3. A product, they're multiplied, of two binomials is exactly what FOIL is for. The firsts refer to the 2x and the 3x, the first term of each binomial. And I'm going to write it out this time, but you might be able to do the product of each pair of terms in your head and just write it down. I'm going to write it down in detail though. The firsts are 2x times 3x. The outers are 2x and 3, so 2x times 3. The inners are negative 10 times 3x. You could just put this negative sign as a minus right here. It saves a little bit of writing. In that case, you wouldn't have to write the parentheses, which it doesn't seem like a lot, but there's a lot of writing, so the less you can do, the better. As long as it's not important enough that you need it. The last part, negative 10 times 3, I'm going to put that as minus 10 times 3. And that's what I mean by avoiding the parentheses, by including that negative as the operation sign. Now the products of all these pairs, the firsts 6x squared, the outers 6x, the inners minus 30x, and the lasts minus 30. And then so you probably will be able to, with some practice, go straight from this to this, because you're doing some things in your head, but you're not doing more than one thing in your head. You have to do the writing to avoid trying to do 4 different mental math pieces at the same time. The next thing and last thing I have to do is combine these two like terms, the x terms, but 6x squared minus 24x minus 30 is the product. And FOIL makes that much quicker than the double distributing. In fact, we probably can avoid that whole line of work. Go straight to writing this down and then combine like terms to finish it. The next thing I want to mention is the perfect square trinomial. So perfect square, I really usually just call it a square, but perfect square, numbers like 4 because it's 2 times 2, 9 because it's 3 times 3, those are called squares, or perfect squares if you're not into the whole brevity thing. What they mean in this case is, for example, x plus 2 squared. I'm squaring this binomial, and what it means is x plus 2 times x plus 2. You can't distribute an exponent to a sum. You have to take that thing that's supposed to be squared and multiply it by itself. That's what square means in arithmetic. So this is a FOIL situation. It's not this times, it's not the pieces times the other. It's all the pieces of this times each of the pieces of this. Firsts gives me x times x, or x squared. Outers gives me x times 2, or 2x. Inners gives me another 2x. And the lasts give me 2 times 2 is 4. And then combining like terms, x squared plus 4x plus 4. That, well, I was multiplying here. I did want to expand this. But that doesn't look like there's square stuff in there. But it doesn't look like it's necessarily the square of one thing. It is, and that's how we got it, but going the other direction is the topic of the next section. Finally, I have one more, similar to the perfect square, a special form called the difference of squares. So again, squares, first of all, think of square numbers, 4, 9, 16, 25, numbers that have a square root that's a whole number. 1 is one of those numbers also. Also, x squared is a square. In fact, x to the 4th is a square because x to the 4th is x squared squared. So squares, there's a variety of different things, but they're all the same thing multiplied by itself, whatever it is. I have an example here to demonstrate a difference. So difference means minus or subtract. Difference of squares. This one doesn't look like a difference of squares. There's a difference, but none of these things are squares. There's x, not x squared. 3 is not a square. But if I multiply these together using FOIL, watch what happens. X times x is x squared. Outers gives me x times negative 3 is minus 3x. Inners gives me plus 3x. And the lasts give me minus 9. 3 times negative 3 is negative 9. And if I combine like terms here, x squared, the leading term is the highest power, minus 3x plus 3x cancel each other perfectly, leaving x squared minus 9. And that is why it's called the difference of two squares. X squared is a square. 9 is a square. 9 is 3 squared. And it's a difference of those two squares. These are going to be more important when we're learning how to reverse this process to unmake the product. That's in the next section. We're going to study the process of factoring, where we'll start with a polynomial and break it down into simpler factors.